Hi, do I have to speak here? I have to. Okay. Hi, very good to be here. So my name is Alexandre Bergel, and so we talk about Agile artificial intelligence. So this is a book that was published in 2020, and and the idea of this talk is to give an overview of this book. So actually, I'm not really interested in doing some advertisement of this book. Like, even if everybody in this room buy 3 copies, probably we won't get nothing from that. But instead, like, I deeply believe this book is a very nice example of where Smalltalk and Faro can really shine. And so I really encourage, any other one to write books. As Steph said this morning, this is very fun, even though this is hard work. So, okay, so this book is about like agile artificial intelligence, and it is divided into 3 parts. The first part is about neural network, and the second part is about genetic algorithm. Like the first part is about like a metaphor of how the brain works, and the second part is a metaphor, a computational metaphor on how the evolution happens. And in the third part, which is called neuroevolution, we combine these 2 things, neural networks, genetic algorithm, and that's pretty cool. So the idea is like I will give very shallow overview of the book with giving some more punctual examples that I think are kind of interesting. So neural networks. So this part of the book like begins with a very simple like model of a neuron, one single neuron, and then it builds up in having a full-fledged deep learning network. So very a network. So here I took the example of the perceptron, which is a model that was made in the 40s, in the late 40s, when when the computer happened, where on earth the first thing they try to model neurons. So a perceptron is like a small bubble here that has a number of inputs. And in that case here I have 3 inputs, x1, x2, x3. And those inputs are numbers. Everything is numbers here with neural networks. And then there is one output. And like in a perceptron, like not all the inputs have the same importance, the same relevance. So there is some. And like you can see that if you take image recognition patterns, the algorithm that recognize faces from a picture, probably the pixels at the border of the picture that do not make they're not really important for the detection algorithm. And for a perceptron, like to have the real relevance of an input is given by a weight. So 3 inputs, therefore we have 3 weights. And the formulas, that give the output of this perceptron is very simple. We multiply x1 by w1 plus x2 times w2 plus x3 times w3. And if this number is greater than another number t, then the output is 1, else it is 0. Very simple things. And, like just an example of, like what this weight is really all about. So, imagine that now here on this weekend there is a, heavy metal concert and you love metal concert, so you really would like to go there. So there is a number of factors that can really help you making the decision to go to that concert or not. Like it could be the weather, if the weather is good, not too hot, not too rainy, and maybe you would like someone to accompany you, and that could be a very important factor for you, for example. And like if you are like me, you don't like to drive, then maybe it is very important to be able to go there without a car. And then you can build models, like on the, so you have like a first model here. Well, can you do that? Here you have this model here where if you have a weight for W1 equal of 2, for the second weight, 6, and then the third weight 2, then you will give much more value to this factor, does someone accompany me? In that case, you really would like someone to accompany you, and this is an important factor for you to go to the concert. Else, you really don't like to drive. In that case, for that model, then it's very important that someone that you can go there without a car. And more a practical example, then here. So more practical example here, you have with this perceptron, you can express the AND logical gate. And so you have a perceptron with two inputs, x1 and x2. So each of these input has a weight of 1. And then there is a threshold, there is 1.5 at the middle. And like if you take a piece of paper, if you just do the math, the very simple math, then you will see that you have a logical AND. You know, like if x1 and x2 has a value of 1, then you have 1 times 1 equal 1, plus 1 times 1 equal 1, equal 2, and 2 is greater than 1.5. Therefore, the output will be 1. Else, if one of the input is 0, then you have 0. And this is the AND logical gate. So in a classroom, I like to say, okay, now take a piece of paper. You want to give a reason with the audience. So take a piece of paper and now try to find the weight and the threshold for, that express the OR logical gate. If you do it, it's not very complex. It will take, maybe a few seconds or a few minutes. It's really not much work. But, like if it just takes a few seconds to find out like these three values, then, like what if now I want to, what if now I have like billions of parameters? This is not something you can do by hand. And this is where all this, learning algorithm really comes into play. Here, this is the simple algorithm that actually like how to find the weight and the bias, this threshold. This is the same word. And yeah, so in the book, I describe that. Also, okay, and here this is the algorithm to actually find the value of the weight and threshold for a given set of inputs. So all the code here is available for free. You can just download it. If you execute that code snippet, then you will install it in your latest Faro. So in that case, this is, so here, like just code snippet that created some, two kind of neurons, one which is a sigmoid neuron and the other one which is a perceptron. And then here you see the learning, the amount of error that the model is making at each epoch, each step of the learning. Again, this is very simple examples, and the book starts with that example. Oops. Okay, so this is so the book begins with the perceptron, and then then here you have the neural networks. Then we describe how we can combine those perceptrons together in order to form something more complex. And then on the chapter 4, there is there is a bit of math. So this is really the part of the book that really gives a lot of math. So I think this is very well explained. So I really spent time on really crystallizing what I learned. And on the chapter 5, then there is some examples, classical example about data classifications. And then like since a neural network, this is bunches of perceptron, this is not really efficient, this is not really fast. So in chapter 6, then we define a matrix library. So the idea is that we do this matrix library in C, and then using FFI, we call that directly from Faro. And then on chapter 7, we adapt this neural network by using this matrix. So again, this is not like, this is some very basic things of what anyone will learn now from AI. Okay, so actually this part 1, this is not really the part of the book that I think is really the crucial things. And but now here comes the second part, where this is where I think the real fun begins. So this is about genetic algorithm. This is a completely different topic than we will mix with the part 1 later on. So genetic algorithm is really rooted in the principle that Charles Darwin put down, such as like to have a species that evolve, then you need to have like this famous law that the strongest element in that species will have more tendency to survive, while the weakest will die. And this is like, yeah, the genetic algorithm is really applied on that. So so we kill a lot of individuals actually. And here a very simple example. So here we have like two friends on the left. The friend on the left hand side say, okay, like let's play a game. So I think about a word and you need to guess what the word is. So this is a 3-letter word. So the the secret word is cat, C-A-T. And then the hero on the left-hand side will say, oh, like as a hint, I will give you the number of correct letters that matches the secret word. So then the hero on the right-hand side will say, like with cow, let's say cow. And cow, C-O-W, has one matching letter with cat. So the score of cow is 1. Then we can make another try, pause. This is not, maybe this is not an English word, but it doesn't matter here. This is just 3 letters. A word made of 3 letters. And then by pause, this score of 0 doesn't has any matching letter with cat. And then the third try, gas also like has the A that matches, so the score of gas is 1. And then we have, we made 3 tries. And the best score we have so far is 1, because gas, like G-A-Z, has 1 common letter with cat. And okay, so this is what we start our algorithm with. We have 3 words, and then we will make this word evolve in order to reach, hopefully, the solution. So then we can apply some genetic operators. So if you remember your lectures in the college in biology, then there is essentially 2 kinds of operators. There is the mutation and there is the crossover. This is how the chromosome can be combined. And then we can combine words pretty much the same way that we combine, that the biology, nature combine chromosomes. And then, we may end up with, can I do that? No. Can I do that? Yeah. Then we can have this CAZ, where you have here the CA that comes, that comes from this C here, and this AZ here. This is how this, you have the C that is plugged in, you have the word gas and cow that gets shuffled, like crossed over, and then it forms CAZ. And then CAZ has a score of 2. And then you may have some other combination that doesn't make much sense, such as the go or the pow. And then, again, then you have a second generation where the best score is 2. Then we can go on, and then you have the best score up to 3, because maybe you have a mutation that will change the Z into the T. And then hopefully, like, you end up with this word cat, the circuit word. So that looks like a very simple, but that's extremely, extremely powerful. And so here, like, this is the example of this is the example of finding words. So I can run that here. And then you see that the blue line, this is the one that maybe the most important, that really gives the fitness of the population. So you see the population of these 3 words evolve, and then here we reach the level of 3, which means that we have found the solution here. So instead of having the 3 words, which is really simple, then why not have like hello ESUG? Then you see that it takes like more, more effort to reach the level of 9, because hello ESUG has 9 letters. So to find the solution, to genetically find the word hello ESUG, then it takes a bit more effort. Then if we can do like, let's say twice, then it doesn't reach it, because it's 15. Then I need to increase maybe the population size. Let's say 2,000 here, and then here it's still a bit better. Here 3,000 maybe. Then here it reaches, so you can play with the hyperparameters in order to steer the algorithm. So this is like one very simple examples where the second part of the book about genetic algorithm begins. Very simple examples. But then this is where things really like become like very interesting. So, oops. So we took, we took very simple chromosome that is made of 3 letters. The chromosome is the length of 3 genes, and then CAT. And each gene, or each value a gene can hold is just a letter. But actually, I can encode anything in a chromosome. For example, like what if, now I'm interested in some, creature that has muscles, and the muscles has the length and the force and the tension and plenty of other things, and to model muscles. And then you can have such example here where you usually try to evolve a creature that is made of a set of muscles, and the muscles can be joined together in order to survive, in order to go further, to move. And this is here what this example here shows. So this is the result of an evolution of a small creature that doesn't know anything, really. Like, it can just move. At the very beginning, it was like very random, but then you see that, so on the right-hand side, you see that there is the blue curves going up. So it means that the model is able to try to evolve a small creature that is able to move. The fitness function here is simply going to the right. And yeah, so, then it also learned how to, how to climb some small stairs. And yeah, and the whole code actually is given and described in the book. And that's, yeah, so there is no call to external libraries. The book is really self-contained. And okay, so then here, this is the result of an evolution of a species, of a small creature. I really don't remember how many generations we went. With the example of the letters, we went through 3 generations. I think here it went through 80 or 128 generations. But then it means that now I should be able to compare different, state of the creature at different, different evolution points. And here this is a different example where it just has to move right. So it doesn't have to climb stairs, but you just have to move right, to the right. And again, here I have different creatures, and each color is from a different evolution point. So you see the yellow one start to begin on the left-hand side. It didn't learn enough how to walk. But then I think the red is probably the fittest one, and the one that comes at the latest evolution. And yeah, so here this is a very simple creature. There is no there is only muscles, there is no skeleton. This is future work, actually. So yeah, and then here you see that this red one is the most evolved one, therefore is the one that can move ahead on the furthest on the right. So it looks like a toy example, but actually it's not. NASA has been really developing kind of robots like that, and they use exactly, almost exactly the same technique, the same algorithm to develop robots that actually can work on Mars. Because the cool thing with those robots, you can really throw them away, and then at some point they will move alone and they will go into one direction. And yeah, so the chapter 9 is really about genetic algorithm, give the principle of genetic algorithm and how to build an engine. And then here, he applies to some classical problems, such as the traveling salesman problem. And that is a very interesting problem, not because of the algorithm, but more the fact that you need to really think about what is a genetic operator. And then we really think about okay, how to improve the genetic operator in order to make things better. Because in nature, actually, when the chromosomes cross over, they do not cross over at any random point. There are some particular point that happens. And the book is, as soon as you try to get closer to what nature has taught us, then it means that we are getting more expressive, more powerful in the kind of problem we can solve. And then here there is, about the exciting maze, and then here there is about how to bring these zoomorphic creatures. As you can guess, all this graphical part is made using Russell. In that case, it's Russell 2. Okay, so we saw what part 1, part 2, and now here comes the part 3, where you combine these two things we have learned before, and about neural evolution. So before talking about neural evolution, just a few words about deep learning. As you have probably know, or at least have heard, all the deep learning techniques that are very greedy in having some data, some training data. So you need to train your model with a lot of data. And it's not just a lot of random data. Your data need to be very well balanced in order to not have biases. And this is very hard to get. And an example, if you want to have a model, image recognition model that is able to tell whether a picture contains a cat or a dog, then you need approximately 2,000 pictures. 1,000 pictures of a cat, 1,000 pictures of a dog. And okay, and then you can build a very efficient model. However, it's not really the way that human learns. And you know, like if you take a baby, then you just draw on a picture what is a cat, then it will recognize a cat. So you know, there is quite some, some step between how deep learning works and how human actually works. And if you look at like the root, you know, the essential papers about neuroevolution, this is really, you know, how can we bridge that gap? How can we make, you know, AI model closer to the way that human learns? Because this is surely to be better. And this is what neuroevolution is all about. Evolution of neural networks is really called neuroevolution. So in practice, you use an AI algorithm to evolve another AI algorithm. In our case, one AI algorithm is genetic algorithm, and the other one is deep learning. So so the third part of the book is made of 3 chapters. The chapter 15 is the longest one, is the most complex one. But the chapter 14 begins with neuroevolution, where you just describe the ideas and easily combine 2 simple algorithms. And then chapter 15 talk about NEAT. NEAT is a well-known neuroevolution algorithm that is, spectacular. And then the really like, it's really beauty, because it's really like how neural networks can evolve from nothing, just from nothing. You have the input that is directly connected to the output, and you see it doesn't work, but then still you may have some neuron, some element in the population that just does a bit better than the other one. Not much, but just a bit better. And therefore, like, the algorithm will try to identify those slightly better individual and make them evolve, up to the point where you can really reach a neural network that is highly sophisticated. And then, so in chapter 15, we just described this NEAT algorithm, and chapter 16, we apply that to an interesting scenario where you can define a mini Mario video games, and then you can let the AI actually solve a level. And I would just here. Oops. I'm almost done. So here, this is, if I execute this code, then I have a very mini Mario game. So the graphics are extremely primitive. It was not really the goal was not to make a Mario, but I can steer that with the keyboard. So there is the platform, and here there is the, like the chimney, the tubes. I can jump, and
where are the coins? I want the money. The turtle, where are the turtles?
They're coming. Wait. Here I'm jumping, and here there is, here there should be one here. Okay, here there is the turtle. Okay, so we try to jump. I lost. But okay, so like in the book, then I described really how to implement that. Again, the goal was not to make, it was just to make something practical that you can, apply the AI algorithm on it. But yeah. And then I think here this is, also there is a level generator, so you can do that. And this is, one level where, this is one level here. So here there is a seed, there is a seed number here I can use, and then you can generate. And the goal of, at the end, then the AI algorithm will have to solve, like to reach here on the right-hand side, the exit. And before I show you that in action, so here this is like, on YouTube you can find, like this experiment that was made using the real Mario game. And the idea is, I cannot see my mouse here. Oops. So the idea here is that on the left-hand side here, this is an abstract representation of the world. Here on what I made a circle, then you have some white pixels and some black pixel. And the black pixel as the monster, and the white pixel are just the platform. And then here you have, at the center, you have this Mario, which is a small red straight carrot. Yeah. And then here on the right-hand side, so which will be the output, is the kind of button you can press on your, on your Nintendo, like you remember, like the the joystick, and then here in between, you have really like the brain. So this brain that connects what it sees on the left-hand side and which button on my joystick I need to press on the right-hand side. So the input is really what I see, and then on the right-hand side is which action, which button on my joystick do I need to press. And yeah, so like the idea is at the very beginning that there is almost no pixel that are connected to the joystick. So it means that, it will not understand to do anything. So like most at the very beginning, like the Mario doesn't even move; it just stays where it does. But if by luck, randomly there is one that just happens to press on the right-hand side, then we just move right. And that element will be better than the one where Mario doesn't move. And then the algorithm will identify that guy here and really make it like better and evolve. And that's really what this algorithm is about. So here, that code here, I will not execute it. This is the one that really evolve this neural network. Instead, I will just show you the result. I do it here. Oops, what happens? Then it just faster than me. That's very true. But then you evolve the monster and until it reaches the end. And the thing is, like, this principle is very similar, to this, very complex model, such as the AlphaGo. So in AlphaGo, where this is an AI that is able like to play Go, where you have actually two actors, and here I just have one. The fitness is to go to the right, whereas in AlphaGo it will be to beat the other one. And yeah, I think I'm almost on time. No, I'm late. But yeah, so that's what the book is about. So all the code here is available for free. What the book is not about. So I think this is very important because the AI is a very overloaded word. So the book is not about complex deep learning models. We do talk about deep learnings, but we don't talk about transformers, which is highly, there is a big hype on that. We don't talk about language models or image recognition. Maybe we could in the future version of the book, but currently the book is not about that. However, the book really will make you an expert in genetic algorithm. I mean, I used a lot of genetic algorithm in my research, and the real book, I think, crystallized all the different techniques associated to genetic algorithm to really being able to use it in a very effective way. And also the book introduced you like to the fascinating world, I think, of neuroevolution. And that is cool. I think this is really the closest things I've seen in computer science that is close to, to Star Wars and other science fiction movies. And yeah. Also, like the book gives some non-trivial and appealing examples. And indeed, like the Mini Mario game, like there is no other book that will go such, such deep. And this is, I think, like where Smalltalk and Pharo are really good for that, because in just like less than 400 pages, then you have a complete book, level generator, and the neuroevolution and the training set. No, that's great. And also the book doesn't really require a strong mathematical background, which is, again, as soon as you talk about AI, this is something that you need to understand, how to derive matrices and yeah, no. Currently, like here, there is no need of that because we're not making deep use of that. So like retrospective and future plan, like the book is made with Russell 2. So I plan at some point to update the book with Russell 3 and maybe to extract the neural network chapters into a separate book. Actually, this part 1, neural networks, is not really the part that I'm the most proud of because I don't go deep and I cannot go deep in that. So yeah, so probably I will squeeze this neural network part because there is a lot of things that is not really interesting. And this is not where I think Pharo can really shine. However, like giving more example about zoomorphic creatures, these small creatures here, like by having a skeleton, and why not to have something that looks like humanoid animals that is absolutely feasible, and also to go deeper into neuroevolution. Currently, like neuroevolution really compete, against state-of-the-art deep learning image recognition models. And I really would like to be able to convey that in the future plan of the book. So yes, so Agile Artificial Intelligence is what I talk about. And also like there is the Agile Visualization with Faro. This is the second book that I've wrote. And in that book, which is about Russell 3, but at the end of the book, there is, I think, a very exciting chapter about reinforcement learning. And really how to visualize the learning using reinforcement learning is very cool. So I really, yeah. Anyway, like tomorrow, I think I will bring few copies of the book. They will be there for, to sell. If anyone is interested, then I will have a couple of copies tomorrow. So thank you very much, and sorry to be late. Thank you.
I have no question. It's a note. I checked the Oxford English Dictionary and boss is there.
Oh, okay, so I didn't know.
Absolute variant of boss, short of positives.
Okay, good. So everything is paused then. Like at the back, maybe? Or?
Okay. The title of the book reads Agile Artificial Intelligence. What does it mean?
Sorry?
What does the word agile mean?
So in the way that I describe it in the book here, we start with a very simple model and we write tests, unit tests for that. And again, that looks obvious, but it's not the case if you take any book about AI, we not talk about unit testing. And the thing is, like, we write books, we write the algorithm, and then we enhance it all the time. That each pages, we make the things better in order to reach, like a model of a version of the algorithm where you can really do cool things, such as what I show you here. So there is this very incrementality in being able to play with it at any stage of the development.
I'm very interested in the video game and been looking into like C++ and other such other utilities. Unity is one of the ones for making video games. And do you see GT any kind of role for where can we make the most of Faro in terms of video gaming?
Okay, so I may not be the fittest guy to answer that question, but I know that there has been quite some effort around Faro to use to make some 3D things, and it can be really impressive. I'm not expert in that. I can't really tell you whether it competes with things such as Unreal or Unity. However, like I've seen several cases where you can really make what looks like a cool video game. And even like on plain desktop, but also using virtual realities. This is also something we did a lot. I did a lot in my past, where we, using augmented reality and virtual reality is really cool. And that really works well in plain Faro. So yeah, so you can do some cool stuff there.
I have a question. Did you find a scenario where the evaluation of the fitness function was computationally very expensive for Faro?
Well, I mean, you could. So in that case, we try to simplify. We try to maybe distribute. The cool thing with neural evolution and genetic algorithms, you can easily distribute that. Right? You can easily distribute that to a cluster. Currently, like maybe something I will talk about in the future version of the book, but currently I have not, because like even the most complex game, like such as this Creature or the Mario game, like it's just 10 minutes of computation on my single laptop. So yeah. So like most of the game, like most of the code given in the book, you can really run it even on your, on a laptop that is not powerful, and that will just work. I don't know who is the chair. Like.
That's me. So next.
Okay. Thank you very much.